All right, so we're in section 5.3, and we're talking about bisectors in triangles. So another reminder, if we haven't done it yet, please, electronics away. So there's one piece of vocabulary that we need to talk about before we talk about our bisectors, and that word is concurrent. So we'll use that quite a bit in the next couple of days. So does anybody in everyday terms, does anybody know what concurrent means? So couple of examples in context when in some of the classes here at Monarch, the students can get college credit in that class as well as get credit for a class in high school. They call those classes concurrent enrollment. Or we could say, like, for example, sometimes when someone is convicted of more than one crime, they're in jail, instead of putting the one sentence at the end of the other sentence, they kind of combine them, and they say the sentences are served concurrently. Does that give us an idea of what concurrent might mean? Yeah?
It's two things happening at the same time.
It's at the same time. So a concurrent in big picture means at the same time. Here, in geometry, we're going to say concurrent is when two or more lines intersect at a point. So that's what we're going to mean by concurrent. We mean the lines are all intersecting at the same point. We call the point the point of concurrency. So over the next couple of days, we're going to talk about several points of concurrency. So concurrent means the lines all intersect at the same point. That point where they intersect is called the point of concurrency. So our first big idea today, these don't have any special name, so I'm just going to say these are theorems. The first one is that the perpendicular bisectors of the sides of a triangle are concurrent at a point equidistant from the vertices. So we said last time if we could have the perpendicular bisector of a segment, that any point on that perpendicular bisector is equidistant from the endpoints of the segment. Well, now we're doing the perpendicular bisectors of the sides of the triangle. So that point where all those perpendicular bisectors meet is going to be the same distance from each vertex of the triangle, each end of the segments that make up the triangle. So let's draw a picture. So we have a triangle, and I'm just doing this by eye here. I'll show you how we do the construction in just a second. we're going to construct the perpendicular bisectors of the sides of the triangle. So I'm going to say this is about halfway, that's about halfway, that's about halfway. And I'm going to draw these in, and then I'm going to erase. So that's pretty close. So we're saying that all of the perpendicular bisectors meet at a single point. So this is perpendicular, that's perpendicular, that's perpendicular. We're bisecting each of the sides, so all of those are congruent. That's how we know we have a perpendicular bisector, 90-degree angle, it's cutting those sides in half. All of those meet at a point. I'm going to call this point P. And what the theorem says is that point is equidistant from the vertices. So I'm going to sketch a dotted line to each vertex. So what the theorem is telling us is that all of those dotted lines are the same length. And since all of those dotted lines are the same length, if we took a compass and put the point there where the perpendicular bisectors meet to a vertex, and I swung it around, it would touch each vertex. What we would get is a circle that fits exactly around the triangle. So we call this point of concurrency. The point is the circumcenter. And it is the center of the circle, the one that I just described, circumscribed around the triangle. Circumscribed means right, scribe means right, circum means around. So we can make a circle that fits exactly around the triangle. So we call that point the circumcenter. Perpendicular bisectors give us the circumcenter. And the circle is the circumscribed circle. Sometimes it's called the circumcircle. So that's our theorem for our perpendicular bisectors. Equidistant, if they all meet at a single point, and that point's equidistant from the vertices. And it's kind of a transitive property with the distances. This distance is the same as that distance, and that distance is the same as that distance, so these two also have to be the same. All right, so I want to show you how we would construct the circumcenter, and I'll show you how we can circumscribe that circle. So let's look at the construction. The construction is done with constructions that we've already learned how to do. We've used them for a couple of different things. So here is my triangle. Can't make it too big. My compass won't fit. All right, so what I'm going to do is construct the perpendicular bisectors of two of the sides. And we know that all three perpendicular bisectors meet at a point. So I'm just going to do two of them. So perpendicular bisector, reminder for that one, that's where we take our compass, open it up more than halfway across the segment, and make an arc. And then we're going to go to the other side and make the same arc. And then I'll connect those points. So there's one perpendicular bisector. And then I'll construct one on the other side. Either of the other sides is fine. So just need to open it up more than halfway, make an arc, make another one. I need to make this one just a little bigger. Go. So there's the other perpendicular bisector, and I'm going to extend it here. Where those two cross, right there, is the circumcenter. So I made the two perpendicular bisectors, they intersect inside the triangle. And now I can make my circle. I just take the point, put it there at the center, put it to a vertex, and if I've done my construction well, it should hit each vertex. That one turned out pretty good. Missed this one just by a touch. If you do the construction really well, your triangle will fit exactly inside that circle. So we say the circle is circumscribed around the triangle. Two perpendicular bisectors gives us a center, and then the radius goes from the center to a vertex. So it's kind of it's a very cool thing that those perpendicular bisectors let us draw a circle around a triangle. All right, questions there? Well, we get another point of concurrency from the angle bisectors. So that's our next theorem. The angle bisectors of a triangle are concurrent at a point. And that point is equidistant from the sides of the triangle. We said last time that if we bisected an angle, that the angle bisector is the same distance from the sides of the angle. Well, now we're bisecting all the angles in a triangle, so those angle bisectors are going to be the same distance from the sides of a triangle. They all meet at a point, a single point, that's the same distance from all of the sides of the triangle. So let's draw a picture for that one. So we're going to do the angle bisectors this time. So we'll bisect, and I'm just doing it by kind of by eye here. Bisect that angle, bisect that angle, that's pretty close, and bisect that angle. And the way we can tell if we have a picture that we have the angle bisectors is all of these angles would be congruent in pairs. So we're cutting each of the angles in half. Well, all of those angle bisectors are going to meet at a point. And that point is the same distance from the sides of the triangle. So if I draw these dotted lines, remember our distance to the distance from a point to a line is the perpendicular distance. And all of those are 90-degree angles. What this theorem is telling us is each of those little dotted segments is congruent. So what this means is if I put my compass point here and opened it up to the side of the triangle and swung the compass around, I would get a circle that fit exactly inside the triangle. So we call the point the incenter. And this point is the center of the circle inscribed in the triangle. Inscribed means written inside. So if we drew a circle using that as the center and this distance as a radius, it would exactly touch each side of the triangle. All right, so let's look at the construction there. So our angle bisectors concurrent at a point. The point is the incenter, same distance from all the sides of the triangle. So we have 2 points of concurrency. Tomorrow we'll talk about 2 others from other things that we do to the sides or the angles of a triangle. And we'll get 2 more points of concurrency. And the really interesting thing is that 3 of those 4 points all are on the same line. All right, so our construction for that one. We have to bisect some angles this time. So we've done our angle bisecting construction a few times. So I need to make this triangle, try to make it kind of small. My constructions for this one don't turn out as well as the other ones. So to bisect an angle, reminder of an angle bisector. We're going to just, from the vertex, we're going to make an arc across the sides. And then we move our point to where the arc crosses the angle. And we need our compass open further than halfway across the angle. Make an arc. Move to the other side, make the same arc. And that will give me 1 angle bisector. Let me draw that one a little more carefully. I want to get there. Okay. And I'm going to bisect one of the other angles. Two of the angles is enough. We know that all 3 should intersect at the same point. So I'm going to bisect the other angle, make my arc. Try to get it to do it without making a full circle. Good. Move the compass point to the arc, open up more than halfway, and make my 2 arcs. And where those 2 cross, that's going to be the center of my circle. So there's my center, my in-center. And I need the distance. My radius is the distance to a side. And we need our perpendicular distance. So the perpendicular distance is, we need the perpendicular from a point not on the line. So that's our smiley face construction. And we bisect the smile. And my radius is going to be this distance here. So now I can set my compass in the triangle. Set it to that radius and draw my circle. This always happens with my in-center. Somehow I miss one side. But if you do your constructions very carefully, that circle should touch all 3 sides of the triangle. My circumcenter is always, my circumscribed circles always come out better than my inscribed circles. But that would be the steps for the construction. All right, questions? The incenter is always inside the triangle. The circumcenter can be in 3 different places. It can be inside, and that happens when we have an acute triangle. So all of our angles are less than 90 degrees. So I'm just going to draw it by eye here. So our incenter is inside an acute triangle. It can be on the triangle if we have a right triangle. And it's going to be on the hypotenuse. So the perpendicular bisector is here and here. So that's going to be on the hypotenuse. So the perpendicular bisector of the hypotenuse goes from here straight out that way. So that's for a right triangle. And it can be outside the triangle for an obtuse triangle. So we have something like that. The perpendicular bisectors are going to go and be outside the triangle like so. So our circumcenter can be inside on a right triangle, inside an acute triangle, on a right triangle, outside an obtuse triangle. The incenter is always inside. Whoa. All right, let's look at some examples using incenters and circumcenters. Let's say we have a triangle drawn on a set of coordinates. So we have some axes here. That's my y-axis and my x-axis. And we have some coordinates. So one vertex of the triangle is at 0, 4. Another vertex is at 0, 0. And the third vertex is at 8, 0. So my triangle is going to look like this. One side along the y-axis, one side along the x-axis, and there's my hypotenuse. Well, since this two sides of the triangle, one's the y-axis, one's the x-axis, what kind of angle is this? That's a right angle. That's a 90-degree angle. So this is a right triangle. And we want to know what are the coordinates of the circumcenter. And we just talked about this. On a right triangle, where is the circumcenter going to end up? It's going to be on the triangle. It's going to be on the hypotenuse somewhere. And we get the circumcenter by where the perpendicular bisectors of the sides intersect. Well, the bisector of this side is halfway between the points 0 and 8. What's halfway between 0 and 8? 4. So the bisector of this side is going to be at 4, 0, and we go straight up. The bisector of this side is going to be halfway between 0 and 4. What's halfway between 0 and 4? 2. So we go from a point 0, 2, and we go over, and we get our circumcenter. Well, how far over have we gotten to get here? 4, and we've gone up 2, so the coordinates are going to be 4, 2 on the hypotenuse, on the triangle. All right, questions there? All right, let's say we're a civil engineer, and in some town that we're working in, we have a mall, and we have the airport, and we have a subway station. And we want a cell tower the same distance from each. Where do we put it? Well, we're civil engineers. Our boss hired us because we engineers are supposed to know some math. So we use our math skills. What if we connected those 3 points? What do we get? A triangle. Let's draw the triangle. So we have a triangle that connects those with the mall, the airport, and the subway at the vertices. We want a point that is the same distance from each vertex of the triangle. What point is the same distance from each vertex of the triangle? What is it? We just talked about it. We only have two choices for what we just talked about. Is it going to be the incenter or the circumcenter? The incenter is the same distance from each side of the triangle. The circumcenter is the same distance from each vertex. So if we were a civil engineer, what we'd have to do is find the circumcenter of this triangle. Where? Put it. So we would construct the perpendicular bisectors of each side and find where they intersect, and that's where our cell tower should go. So it would be the same distance from the mall, the airport, and the subway.
Attention staff, the first bell didn't ring for lunch. So there may be students that are exiting the gym and the courtyard coming in late because the bells aren't ringing properly.
Okay. All right, questions there? All right, let's look at one last example. Here's our setup for this one. And I'm going to draw some other pieces here. All right, and based on just the drawing that I have so far, these lines, what are those lines doing to the angles of the triangle? Bisecting. So the blue lines are angle bisectors. So I'm going to call this point G. So where those angle bisectors meet, what is that point? Angle bisectors, same distance from the vertices or from the sides? the same distance from the sides or from the vertices? Angle bisectors? From the sides. So point G is the incenter. It's the same distance from all the sides. So now if I had a problem that looked like this, and this was point F, and this is point B, and this is 8x minus 7, and this is 5x plus 8. What would we know about those two lengths? They have to be the same. Those are the distances to the side. So if the problem says find GF, well, we know that these two are the same. So 8x minus 7 has to equal 5x plus 8. Subtract 5x. 3x minus 7 equals 8. Add 7 to both sides. 3x equals 15. And x equals 5. And the problem says find GF. So GF is 5 times 5 plus 8, which is 33. And that should turn out to be the same as the other segment. 8 times 5 is 40, minus 7 is 33. All right, questions there? Okay. All right, there's that.